Finally, we are already on the very last method, numerical method that we're going to discuss. So, diba sa shooting method, we are going to convert the ODE. Let's say if it's higher than the first order, ato siya convert in such a way nga may mo siyang a lower order. And then we are going to convert the boundary value problem to an IVP. Here in the finite difference method, we are going to convert the ODE into a system of linear equations. So, dali na lang siya. So, di ba, we have already discussed the finite difference method last time on numerical differentiation. We have the forward, we have the backward, and then we have also the central difference. So, for this one, we are going to apply the difference method, the finite difference, in the interior points within the curve. So, in this method, the derivatives in the differential equation are placed with finite difference method. So, CODE is converted into a system of linear equation by applying the finite difference approximation. So, we have here the points. We have the given conditions by endpoint, the boundary conditions, and then kani sila sa sulod, we call this the interior points or interior nodes. So, the domain of the solution of the interval A to B, or the endpoints, is divided into n subintervals. So, more definition, we will introduce step size for this one in this form, the B minus A all over n. Then this would be equidistant. So, the DE is then written at each of the interior points. So, kaning tanan interior points, kuhaan nato ni siya, og we are going to apply finite difference in the interior points. Ang mahitabo din anin ni siya, ma-convert din ni siya, mahimo din ni siyang system of linear equations. And kabalo naman ta, diba, to solve a system of linear equations, we have already several methods. We have the Gaussian elimination, we have the Gauss-Jordan, and other methods. And for better accuracy, we are going to use the central difference formula for this one. So, diba sa central difference, if you remember, this is the central difference approximation. Ato lang itong gisulat last time as this one, f of x plus h minus f of x minus h all over 2h for the first derivative. And for the second derivative, ingani yung itsura, f double prime x is equal to f of x minus h. Iya lang diri nga form this, ingani niya pagsulat. Minus 2f of x plus f of x plus h all over h squared. So, tanan ka to siya ang second order. We're going to convert it into this one, but that is just the point. So, with the same example as we had with the shooting method, now let's solve this one applying the finite difference. So, since we know using the central difference, diba, the second derivative is this one, diba? So, we can rewrite this second order differential equation into this form. So, nganong tema ni ang nadiri, it is because this is the dependent variable. So, ang sulod diri are the dependent variable. Same also with this one. And then the h part, the h squared, again, diba, it can be written as delta x. Sometimes we write that as delta x or h. No, they are just the same. They are just equal. They all mean the same thing. That is b minus a, the upper minus the lower limit, all over the number of intervals. Since we rewrite, since this is the central difference nga kuan, second derivative, we can apply it to this equation. So, nawala ng ODE dira when we substitute it. So, it will look like this. And then, if we distribute this, if we transpose this part and then distribute the h, we'll have this equation, and eventually we can summarize it in this form. So this is constant, this is as well as constant, this is the initial condition, this is the end condition, and this is our step size h. Sa ato pa kani sila, this is constant, and this part here is also constant. Ang mag-change lang is kani, this one, and this one per node. So again na itong gamitan ani is kada node sa kuan or kada interior points. So this will be the general form of this equation. So since our step size is 2, so kada node, the first interior node is when x is equal to 2. So diba we have x dot is 0 and then the step size is 2. So nga niya siyang may tabo. We have 2, 4, 6, 8, and then lastly is 10. So itong kuhaan ani of finite difference is the interior nodes. So this is the first. And then we'll have this equation na ma-form. At second node, when x is 4. At third node, and lastly at the fourth node is this one. So matikod mo, we have the T0, T1, T2, T3, and T4, and then the T5. So we can form this system of linear equation, and then we can solve this one by applying Gaussian elimination. So diba, dali na lang kayo. The form. So this is a 4x4 nga kuan coefficient matrix. So this is almost a kung ano katong triangular nga kuan matrix. So we just have this. Then from here we can solve everything. So applying Gaussian elimination, and then we can have this one as our solution. So for the T1, T2, T3, and T4. And then from here, we can see that at each nodes, at when x is equal to 2, the t is 65 or almost 66, and x is equals to 4, is equals to 6, and x is equal to 8. These are the corresponding values of the t.